All right. Hello and welcome to Refactoring with Cognitive Complexity. Thanks for joining us. I'll get started now. I'm going to start with some housekeeping details. First, this will be a 45-minute session, including demo and Q&A. Please go ahead and queue your questions in the Q&A box. We've got Colin and Aaron from the SonarSource services group to queue your questions, triage them, and feed them to me at the end. We are recording this presentation, and in a few days you'll get an email with a link to the recording and all the Q&A. So even if I don't get to your question live, you will get a link to the answer afterwards. And finally, once the webinar ends, you'll get a feedback survey. Please do take the survey. Please tell me how I did. Tell me what you liked, what I need to work on, and what SonarSource should cover in future webinars. Okay, so the agenda is I'll start with some introductions. I'll talk about why we formulated cognitive complexity. Then we'll look at what cognitive complexity is. We'll talk about the validation that's out there. Then we'll get into refactoring, why we're all here, and then we'll talk about what's next. So my name is Ann Campbell. I am the primary author of Cognitive Complexity. I have coded in a number of languages, and I brought all of that experience along with the experience of my colleagues into writing Cognitive Complexity. Now, if you're familiar with complexity in a programming context, you're probably most familiar and have most used cyclomatic complexity. That was released in or published in December of 1976. And its aim was to measure understandability. What it really does well is measure the number of test cases that you need to fully unit test a section of code. What it really doesn't get at is understandability. And at SonarSource, we really felt a need for a metric that would help us gauge that. So that's why we undertook cognitive complexity. Now, I want to illustrate that with a couple of examples here. So first we start with sum of primes, and these examples are straight from the white paper. So sum of primes has a cyclomatic complexity of 4. So +1 for the method structure, +1 for each for, and +1 for the if, total of 4. Now contrast that with get words. So again, +1 for the method structure, and then +1 for each case in the switch for a cyclomatic complexity of 4. So these two methods have equal cyclomatic complexity, but I think it's obvious that they don't have equal understandability. And that's why we felt the need to create something else. Now, cyclomatic complexity, it works off of mathematical formulas. And so I think you see here that for judging understandability, mathematical formulas don't really do it. So instead, cognitive complexity has guiding principles. So the first guiding principle is to ignore structures that allow multiple statements to be readably shorthanded into one statement. The primary example of that is the method structure itself. Assuming you put a good name on your method, then that's what you've done when you create a method. So we're not going to increment for the method. We also don't increment for things like the null coalescing operator that some languages have. That's once you understand the syntax, that's really easy to read, and so we don't increment for it. We do increment for each break in the linear flow of the code. The idea here is that ideally you would be able to read code like a novel, top to bottom, left to right in an unbroken flow. When that flow is broken, when you have to do something other than top to bottom, left to right, then we increment for that because it makes you work harder. We also increment when flow breaking structures are nested. So I think it's intuitively obvious here that if I have 5 if statements in a row, that's easier to understand than if I have those 5 if statements successively nested. And that extra work that you have to do to understand that nesting is what we're trying to take into account when we increment for the nesting. Now, a lot of people want to know, okay, well, give me the specification. So really quickly here, I'm going to go through it. We increment for breaks in the linear flow for branches. So if, else, ternary, catch, and switch. For loops, so for each, while, do, while, and each method in a recursion cycle. Yes, recursion is a loop. It's sort of a meta loop, but it's a loop. We take that into account. We increment for jumps to labels, so go to, break, and continue to a label, and we increment for sequences of like binary logical operators. For nesting, these are the things that increment the nesting level. So if, else, ternary, catch, switch, for each, while, do while, and nested methods and method-like structures such as lambdas. Now, again, we don't increment for having a method, but when you have a method inside of a method or a lambda inside of a method, then we start counting the nesting. These are the things that receive a nesting increment. If, ternary, switch, catch, for each, while, do while. This will all make a little bit more sense when we start looking at code. There are exceptions to these rules. So for instance, COBOL does not have an else-if structure. Typically what you'll see in COBOL is an if with an else, and there's nothing inside the else but another if with an else, and there's nothing inside the else but another if with an else. So not having that structure doesn't mean that COBOL programmers don't have the need. They have to work around the limitations of their language. And if we incremented in COBOL for that type of structure, it would really just be unfair. So we're not going to penalize COBOL developers because of what their language doesn't have. So there's an exception for that. Similarly, up until relatively recently, JavaScript didn't have a class structure. And so JavaScript programmers used sort of a pseudo class structure. Even today, there's a lot of extant code that uses that pseudo class structure. And there are a number of frameworks that still today require you to program with a pseudo class structure. And so there's a specific exception for JavaScript. Similarly, there's an exception for decorators in Python, and we consider additional exceptions as we come across needs in specific languages, but all of the exceptions are language specific. What's not included in cognitive complexity is hard language features, such as pointer indirection, templates and generics, multiple inheritance, etc. The reason for this is that way lies religious wars. So I used to program C. For me, 2 levels of pointer indirection is routine. But once you start getting into 4 and more, then it starts getting hard. But deciding where it gets hard is really very much a judgment call, and we just didn't want to get into that. So hard language features are not included in cognitive complexity because cognitive complexity is about control flow. So this is really about how hard is the control flow of your code to understand. So coming back to my examples, and I said that this would start to make sense once we could started applying this to code. So coming back to sum of primes, let's look at the cognitive complexity. So we've got this first for loop, which is +1 for the for. Then inside that, we've got another for loop nested. So that's +2, 1 for the for, 1 for the nesting. Then inside of that, we've got an if. That's +3, 1 for the if, 2 for the nesting. We don't do nesting on the jump to a label, so our continue to the out label is just +1. And that gives us a total cognitive complexity on this method of 7. Now contrast that with get words, where we've got a switch and 3 cases and a default, and that's +1 for the switch in all its cases. And so we have a total cognitive complexity on this method of 1. And so now just looking at the numbers, I can understand immediately which of these is going to be more difficult to understand. And that's what we were trying to get at with cognitive complexity. So validation. Up until last summer, you could have very validly said to me, it's just your opinion. You know, how do you know that this works? So I was very relieved last summer to see that a paper was published which actually looked at the validity of cognitive complexity. And the authors found that it is actually a good measure of source code understandability. I've lifted some quotes from the paper here. So the authors found that cognitive complexity is a good indicator of how long it takes developers to understand a piece of code, and that code snippets with higher cognitive complexity are rated by developers as more difficult to understand. They also said that since developers spend a large time a large portion of their time in maintenance, very few of us get to write greenfield code, that it's worthwhile to make the code easier to understand, and that cognitive complexity can help you find the pieces of code that need work. They also said that it's not proven yet how much cognitive complexity is too much cognitive complexity. Personally, I'm very much looking forward to someone taking this topic up and publishing a follow-up paper. Fingers crossed. So now what we're all here for, refactoring. So the reason that this is mainly focused on refactoring is that I personally don't find it particularly helpful to be able to point at something and say, that's bad, without knowing how to make it better. So that's why that's the primary focus here. In the years since we published Cognitive Complexity, I've come up with a few different patterns that seem to me the best ways to approach reducing cognitive complexity and therefore making the code easier to read. So the first is invert a condition and use an early exit. Sort of a corollary to that is eliminating the else clause. These two things help you reduce a lot of nesting. The next thing is structural collapse. Now, this is not what happens in an earthquake. This is when you have an if with nothing inside it but another if, and potentially even more than that. And so what you can do is and those conditions together and only have a single if. It makes it easier to understand. The next one is extracting methods. So sometimes you're looking at a method with a gnarly piece of code in the middle that you can't do much with, except extract it to a new method and put a readable name on it. So again, do readably shorthand multiple lines into one. That can be very helpful sometimes. Similarly, if you're doing the same thing over and over again, then that's a cause for extracting a helper method. And finally, language features. So there's nothing specific here. This is about knowing what the features are in your language that are easier to understand than other ways of doing it. You know, as programmers, we know that there's very often multiple different ways to write the code. And so this final one is about knowing which ways are easier for the person who comes behind you to understand. So it's time to get into refactoring. And my job here is to make things, wait, this is the wrong GIF. My job is not to make things as difficult as possible. My job is in fact to make things as easy as possible. So let's do this. So I'm going to first jump into, whoops, did not mean to do that, Sonar Cloud. So Sonar Cloud is an online service to provide static analysis to help you improve the code quality and code security of your projects. And I'm looking at an issue in an open source project. Sonar Cloud is free for open source projects. And I've got an issue here, a cognitive complexity issue. And I've got secondary locations to help me understand where the cognitive complexity is coming from. So for instance, there's +1 on this else. Else's don't receive a nesting increment. We've already paid that penalty on the if. So this if is +4, 1 for the if, 3 for the nesting, all the way down here to secondary location number 20, which is +10. And so I've got a total cognitive complexity on this method that's 65. And when I look at what the method is, I see I start with an if and I have an else with nothing in the else but another if, and an else with nothing in the else but another if, and so on. And so that pattern may sound familiar to you from when I was talking about the exception in COBOL, because in COBOL you don't have the else if structure, but this is Java and you do have the else if structure, and so there's no exception. And so we count up all of this cognitive complexity and it adds up really fast. So this is a great example, and they're not usually this clear cut. This is a great example of a place where structural collapse can really help. What you can do here is turn this all into a single if-else if tree. And I counted it up once. I think it adds up to 13 if you were to collapse this all into a single tree, and that includes the +1 for our binary logical operator sequence. So that's what I wanted to show you in the browser. Now I'm going to jump into the IDE here. So first, I am in IntelliJ's IDEA. and I'm using SonarLint. SonarLint is a free and open source IDE plugin. It's available for most of the IntelliJ IDEs, as well as Eclipse, Visual Studio, and VS Code. So down here at the bottom, I've got the SonarLint pane open, and it's showing me all of the issues that are in my current file. So I'm going to click on my cognitive complexity issue, and it takes me to the issue in the code, and it highlights my secondary locations for me. It also shows me my secondary locations here on the right. Now, by default, the first tab in this part of the pane is the rule itself, in case I don't understand quite what's going on. But I can also have easy access to the secondary locations, and I can see the message for each location. I can also see the message if I mouse over it. So here at this first 4, it's +1. By the time I get down here to this if, it's +5. Now, this issue, I'm at 16 versus the 15 threshold allowed. That's the default threshold that we set in the rule for Java. And anytime you have a rule that includes a numeric threshold, the threshold is going to be somewhat arbitrary. And so it would be really easy to look at this and say, well, 16 isn't that much worse than 15. Do we really need to do something here? And, you know, sometimes that's going to be the best answer. But it's worth looking at it first to see if there's something simple you can do to clean it up before you move on. And so when I look at this method and I look at where the cognitive complexity is coming from, I see this deeply nested indenting here. And here in the secondary locations list, I see that most of the cognitive complexity is coming from nesting. And so if I can reduce some of that nesting, I can very easily get below the threshold. And so I start here at the top with a for loop. There's not a lot I can do with this for loop. So, you know, a lot of times when you're dealing with loops, your best option is to extract the code inside to another method. But this is already, you know, a nice compact method. This is not a huge method. It's just that there's a lot of nesting here. You know, maybe I could invert this condition and do an early return. That's an option here. But I also noticed that at the bottom here, with the highest level of nesting, I've got an if, and there's nothing inside it but another if. And so that's a prime candidate for structural collapse. So if I just and these two conditions together, and let me clean up the curly braces, and whoops, also have to clean up the if. And if I outdent this just to make it clear what's going on here, then I've already dropped enough complexity to get me below the threshold. So I could happily move on here. If I wanted to go further, I could invert this condition. Now, I can't do an early return here, but I could do a continue. And let me outdent this and clean up the curly braces. Whoops, went a little too far there. And hopefully you'll agree that this code is a lot clearer just with those small changes. So that's what I wanted to show you there. Moving on. So I've got two issues in this file. I'm going to start with the second one. So I click on the issue, SonarLint takes me to the issue and code, highlights my secondary issues. And with this one, I see that I'm at 19 versus the 15 threshold. If I look at the secondary locations, I see that I've got a lot of nesting points here. So +3, +4, +4, 3, 4. So again, if I can reduce some of that nesting, that's going to go a long way to cleaning this up. So then I come back and I look at the code, and I see that basically the first thing I have in this method is an if. So let's see. And it turns out that nothing happens in this method outside of the if. So this is a really great case for invert the condition and do an early return. So if, wait a minute, did I just do that right? It was already at not. Whoops, sorry. I'm moving a little too fast here. All right, so let's invert the condition. So equals null. So if the tag equals null, I want to go ahead and return. Otherwise, I can do the method. Let's outdent this and clean up the curly braces. All right, and so already I think it's a lot clearer what's actually happening in this method. If I have a null tag, return, otherwise do these things. I could try to go a little bit further here, but I think this is enough. So now moving on to the next example. Here I'm also at 19 versus the 15 threshold. And when I look at the secondary locations, I see I've got a lot of +4s, +3. So again, we're looking at nesting. If I can reduce the nesting here, it's going to simplify the code, make it easier to understand. So when I look at the code itself, I see that I'm starting with a 4. Now, there's no way that I can invert this and do an early return. So there's my favorite trick out the window. But if I look a little bit further at the code, I see that I have inside the 4 an if, and nothing happens outside that if. And I've got another if, and nothing happens outside that if. So I've got two things that I can apply here. So first of all, I can do a structural collapse here. I can AND these conditions together. And let's clean that up and clean that up, outdent it just to be clear on what's happening. All right. And so that already makes it a little simpler. And then I also have this if and nothing happens outside the if. Now I can't do an early return here. I don't want to return early because we've got to test the next value in the for loop. But I can do an early exit out of the loop. TINUE. Let's pretend I can spell. So let me outdent this and clean up the curly braces. All right, and so now I'm well below the threshold with an easier to understand method. So moving on to the next one, I've got one issue in this file. And when I look at it in the secondary locations here, I see +2, 3, 4, 5. So that tells me that I've got a successive nesting here. And so then I come back and I look at the code and we start with an if and then an else. And then let's see, nothing happens outside the else. So let me come back here. If this condition set result, and then we return the result. Okay, so why don't we go ahead and return the result instead of setting it? So return. All right, so now if the condition is met, I'm going to return. So I leave the method. That means that I no longer need this else clause to guard the rest of this logic. So let me clean up the curly braces, outdent this, and there we are. Then I look a little bit further and I see that over and over again, what we're doing in this method is setting result, and then nothing happens after the set except that we finally return it. So I can start sort of from the inside out here. Let's go ahead and return this one. And then I no longer need this else to guard the rest of this code. And I can go ahead and return this one. And so then everything that happens in this if, every path ends with a return. And so I no longer need this else to guard the code. And so on. So I'm not going to do that for every path through this code. I think you see the pattern here at this point. But if we went ahead and turned all of these sets into returns, then that's going to greatly simplify the structure of this code. Okay, so moving on to, oh, well, I'm still at 16. Okay, I'm going to do it one more time, just so I can get below the threshold. And that should take us below the threshold. Issue goes away. There's still a little bit more work to be done. All right, so moving on to the next one. So when I looked at this file, I saw that I had two issues here, one at 41 and one at 42. So I start by looking at the first one. And I see that we start with an early return. That's good. I've got some binary logical operators here. Then some more binary logical operators and another early return. Early returns are good. Another early return. Okay, so then I come here and all right, nothing happens outside of this if. So I could invert this condition and do an early return. I've also got nothing inside this if, but another if. So if I wanted to move these sets to outside of this if, I could do a structural collapse here, but there's probably a reason it's structured like this, maybe for readability. So I'll just leave that alone for a second. So I could do an early return. Early returns are really helpful when you're, well, it makes things clearer. But in terms of refactoring for cognitive complexity, it helps to reduce nesting. But really, most of the complexity in this method, and I'm just going to expand the pane down here, comes from all of these binary logical operators. I have 38 secondary locations, one for almost one for each time the operator changes. And so even if I invert this condition and do an early return, that's not going to do a lot to get me from 41 to below the threshold. So probably I need to figure out what to do with all of these binary logical operators. And I'll be honest with you, when I was first evaluating this file to see if I wanted to include it in this webinar, I looked at this and I said, I'll come back to this. And I went to the next method. And so I started looking at the next method and I found binary logical operators with an early return. We've got a try, another early return, another early return. And then I found this chunk of code, which looked very familiar to me, to the point that I put the files, two copies of the file side by side so that I could verify that it was actually two different methods and that something hadn't gone wrong in SonarLint and it was showing me the same thing twice. This is actually two different methods. The logic is slightly different between the two. So there's a reason there are two different methods. But what I come to is that I have this big chunk of gnarly logic in the middle here that, you know, there's not a lot useful I can do with this except maybe extract it to another method. So I'm going to do that in this one because of the signatures of the variables. So if I extract this, and I did my homework, a good name for this is collinear overlapping. Now, if this were actually my code base, this is a code base that I found on Sonar Cloud. If this were actually my code base, I might have an even better name for this. But based on some of the names in the code, that seemed like a decent name. So now I can take that method call and drop it in here in this other copy of the logic, because it is the same logic twice. And now SonarLint recalculates, and I've eliminated one of my original methods, and the other one is down to 16. Now that one's down to 16 because it has this extra try catch, and we do increment for the catch. So in this case, you know, I still have the option, well, no, I can't invert this condition and do an early return because I'm already early returning here. So in this case, I would say, you know, 16 isn't that much worse than 15. I'm just going to leave this alone at this point. But I do still have this 24. I'm going to pull it up in the left-hand pane. And, you know, if I could reduce this 24, I would feel even better about the refactoring I've done. And really, again, it's down to all of these binary logical operators. And so I stared at this for a while and I realized there was a pattern, and I'm going to rearrange this just a little bit to hopefully make the pattern a little bit clearer to you. So the pattern I saw was that we've got pairs of comparisons. So I've got x-axis 1, and I'm looking to see if it's between x-axis 3 or x-axis 4, whether 3 is first or 4 is first. So this set of comparisons is to see if 1 is between 3 and 4. And then this one is to see if 2 is between 3 and 4. And then if to see 3 is between 1 and 2. And then we do that with the y's. And so here we're doing the same thing over and over again. And so that's a case for a helper method. And so rather than making you watch me type that, I did it ahead of time. And so here's what that turns into. So is collinear and overlapping a slightly better name than the first one, with a calls to the helper method. And so now with a really good name on that logic that I've extracted into the helper method, this operation here, this logic becomes a lot clearer. Now it's not just this mass of comparisons that I have to read one by one. Now I understand that I'm looking to see if x1 is between 3 and 4 and x2 is between 3 and 4, or, excuse me, not and, but or x3 is between 1 and 2, and then the same with the y's. And so hopefully, if I put these side by side, so here's where I'm calling a version of my helper method. So let's just switch to the one with a better name. Hopefully you'll agree that this is far easier to read and understand what's going on, which is the whole point, what we're trying to get to. Now I've got one more example for you that's in a different project. Again, I found this project on Sonar Cloud, open source project. And I've got one method in this, one issue in this file. Let me pull this up on the left, just because I prefer to work on the left. So here. So I've got one issue in this file. And if I look at the secondary locations, I see I've got a +1, then I've got a series of +2s, and then some +1s with one more nested something here. So then if I come back to the code, I see I've got an if, and then inside that, I've got a series of nested ifs, and all of these nested ifs do an early return. That's not bad. And then I've got sort of a default case. So if I fell into this first if and none of these others worked, then I do this last thing. And then I've got a series of else ifs. So I've got an if else if tree. And a lot of my complexity here is coming from this series of nested ifs inside of the first if. So looking at this, trying to figure out if there's something I could do, my first thought is there a way to make this part of the top level if else if tree? And I realized there wasn't really a good way to do that. But looking a little bit more closely, what I realized is that each one of these ifs tests the same variable against a different hard-coded value. Well, that's kind of the description of a switch statement. And as a Java coder, I know that since Java 7, I can switch on a string. And cognitive complexity counts each if individually. It increments each time for each else if in an if else if tree. But for a switch, it increments 1 for a switch and all its cases. The reason for that is that switches are easy. A switch tests one variable against a set of hard-coded values versus all of these ifs, which I have to read every single one to understand what's going on. If I look here, I still have to read every single one. Now, it happens in this if else if tree that they all seem to be testing the same variable. But I don't know that until I read it, because it doesn't have to work that way. It could test entirely unrelated things, or it could test additional conditions. But a switch tests one variable against a series of values. And so I can convert this series of ifs into a switch. I've done that here on the right. So on the right, I've got a rewritten version of the original method that had the issue in it. And so I turn this into a switch, and I realize that I'm able to extract some of the common operations. So the creation of the exception that I'm going to throw and setting some of the common values. Now, I'll be honest with you, in doing this refactoring, I went a little bit further than pure cognitive complexity would have led me to do. Because as I worked on this, SonarLint prompted me with things like, hey, these two cases have exactly the same body, maybe you should combine them. And so that's what I've done. So I ended up with a really clean switch here that's, I think, far easier to understand than the original code, which again is the point. So those are all the examples that I wanted to show you, and I'm going to jump now back to the slides because I have a few more of them. And here we go. So the first thing to say here is that what you've seen me do is dig into old code to find things that I could clean up. Now at SonarSource, that is typically not the way we advise you to operate. Instead, what we really think is the best way to go is to clean issue code. So don't dig up old issues to fix them. I had to do that to find good examples to show you. But generally, when you're looking at refactoring yourself, wait until you actually have to work on the code and then look at refactoring it, because let's face it, to be able to work in the code, you had to understand the code, and now you're in a great position to do any refactoring that needs to be done. Alternately, when you're working in code and SonarLint raises a brand new cognitive complexity issue, the code is fresh in your head, and that is when you want to fix any newly emerging cognitive complexity issues. So ideally, rather than digging up old issues, you're going to be refactoring with cognitive complexity in SonarLint issue code, or maybe in your PR analysis before you merge into the main branch. Or even before you release into production. That's a little bit later, but still in a good place while the code is still new and it's still owned by you. You can go in and fix what was there. So I needed to say that to you. So now what's next? So here are some of the resources that I've referred to. There's the white paper. And again, you'll get these links in the email that you get as a follow-up in a few days. I've also given you the link to the study that I referenced in case you want to read that yourselves, and a link to a blog that I wrote on the Clean as You Code methodology. So if you're not already familiar with this, please go familiarize yourself and then drop into the SonarSource community, which I didn't give you a link to here, but I will in the email, and let me know if you have any questions about it. The next thing to do would be to actually get started in your code. So you can go to sonarlint.org to learn about SonarLint, or you can go to your IDE's marketplace to go ahead and get it installed. And you can get started with Sonar Cloud, which is what we looked at earlier, which is in the cloud, and then Sonar Cube, which is an on-premise option for code quality and code security. All three of those have fully implemented cognitive complexity. And now it's time for questions, if there are any.
Hey, Ann. Yeah, we have a couple of questions from the audience. Here's one that was really interesting from Amare. What's the main reason to consider simple ternary and if-else structures as equivalent in complexity?
Well, because they do the same thing. Really, a ternary structure is an if-else-if structure, just with different syntax. And honestly, if I could increment extra for a ternary, I would. And okay, I'm the primary author, I could have, but we agreed to only not do partial increments or double increments. It's +1, but really, what we're looking at is measuring when the code is not readable, understandable, as an incentive to making it more understandable. And a ternary operator, I personally find to be even less readable than a normal if-else structure. So hopefully that answers it.
Awesome, thank you. And then we've got another one here from Georgios. I think this is something you touched on, but he had an interesting way of asking the question. Would it make sense to lower every statement to its base form, i.e., instead of a switch or a sequence of if else instead of a ternary operator and if else, essentially removing syntactic sugar?
If I understand the question correctly, it is going to make sense to use the most readable form. Now, in terms of syntactic sugar, I think a null coalescing operator is a really good argument against that, because a null coalescing operator is basically, let's see, I should have opened this tab. And I don't have my bookmarks available. So basically, with a null coalescing operator, I say variable A equals null if condition set A to some value, right? And a null coalescing operator allows me to condense that into one statement. And once you understand the syntax, then you read it like this versus having to actually read, okay, variable set to null, do the test set to a value. Right, so that syntactic sugar is actually easier to read than the basic form. And so I don't think that there's a blanket argument for reducing things to their lowest forms, personally. So what's next, Aaron?
Okay, I've saved the provocative question for last. Is cyclomatic complexity obsolete?
Okay, so it depends on what you want to do. As I said earlier, cyclomatic complexity, if you read the original paper, was formulated in an attempt to measure understandability, and that's not quite what it ended up doing. So in that context, yes. At the same time, it's not without value. It does give you an understanding of how many tests you need. And so there are contexts when it's still valuable. On the other hand, we've got really good tooling today versus in December 1976 for tests, right? So it's super easy now to understand what parts of code are uncovered, how well covered things are. And so I'm reluctant to throw shade on another author's work, but I think there's less need for cyclomatic complexity today than there was in 1976. So you said you saved the provocative question for last, Aaron. Does that mean there aren't any more questions?
I think that's it.
Okay.